Let's move now with the last presenter, and afterwards we will open the roundtable discussion. I'm very honored to have here at this virtual seminar Freek Bos from Eindhoven University that will provide us still new applications with a presentation titled Structural Design and the Validation of Layer Extrusion 3D Printing Concrete. Some case studies, so it is a privilege to have the possibility to work with different case studies. And Freek Bos is an assistant professor of concrete structures at the TU Eindhoven in the Netherlands, and he has been involved in 3D concrete printing research since 2015, and he specializes in structural engineering and reinforcement for 3D concrete printing. I have to mention that he recently completed the second International Conference on Digital Concrete that was hosted at his university in Eindhoven, and I should say it was extremely successful with a lot of people that joined it. I think also with a lot of outcomes in terms of proceedings, but also special issue papers. And I really thank Freek for being here. So welcome, Freek, and good luck for the presentation.
Thank you very much, Costantino. I hope you can now see my screen. So my name is Freek Bos. Thank you for the introduction. I'm assistant professor at the TU Eindhoven, and I'll say something about some projects that I was involved in with layered extrusion 3D concrete printing. So this, as you see here, is the process. I think to many people now starting to be a bit familiar. We have a nozzle where there's a filament coming out. And these videos are about 4 years old now. These were still early experiments at the TU Eindhoven. But the technology has really taken off since that time, so much so that we see all these kind of new projects emerging around the world. Small buildings, like one-story buildings, mostly they're still conceptual and case study like that. They're not really used, but more showcasing the possibilities. But there are also already some examples that are really in use, like the two examples on the left that you see here, the a drone laboratory in Dubai and a meeting room in the Netherlands. They are both really actual in-use buildings. And this is a technology that is developing further and further, and so the scope of projects is growing more ambitious. Apple printed a fairly large building in Dubai. So you see also that we're now moving from one story to more stories. Now two usually. There's another example here from Belgium, so there's a growing ambition, not only in terms of buildings but also in terms of infrastructure projects. On the left you see a small bridge that I'll be talking about a little bit more, that we were involved in, bicycle bridge obviously, as it is the Netherlands. And on the right hand side you see pedestrian bridge that was completed in Japan, actually one of the winners of the best paper award at the conference Digital Concrete that we had last week. A very clear interest to really start using this technology in the build practice, but that raises questions. These projects need to be engineered. There need to be a structural engineer who is working on them. And if you work as a structural engineer on projects like these, you're confronted with a whole bunch of problems and unknowns that you have to make decisions about. Globally, I divide them in three groups. There's some issues about material and process. First of all, most clearly understandable is probably the anisotropy between the layers. We don't fully understand yet how big the strength differences will be respective to orientation. studies that are going into that have not really been aligned in their results. So initially, I think there were a lot of publications that showed a very big difference in the strength of the let's say across the filaments, respective to in parallel to the filaments. But some later studies seem to suggest that this can also have something to do with the printing conditions, and it is also seems to be pretty dependent on the material characteristics of the print mortar that you're using. So there's still some question marks about that. And then issues like creep and shrinkage and durability are very hardly been touched upon in research yet. And they are very relevant, considering that when you're printing, during the curing, there's no protection from dehydration, and that can have a negative influence. And in addition, the material itself has a high cement amount, which increases shrinkage as well. So a lot of questions mark there still. And then there's the other group of problems you encounter as structural engineer, which is the calculation input. They're obviously related to the question marks on material, but it is questionable what kind of materials data you can use in your analysis. What kind of structural behavioral data, like if you can compare it to structural engineering codes on concrete, there's quite a number of equations are empirical equations, so they're based on experience in testing, in shear, for instance, and that data is just not available yet for printed concrete. And then there's the geometrical data, which is also a bit vague, because how well do we actually know the width and the height of the layers that are being printed? So, for instance, we've experienced that if you print like one layer, then you can measure and say, okay, well, the width is maybe 4 centimeters or 5 centimeters. But if you start stacking a whole bunch of layers, like hundreds of layers, then they will all sag and the width will increase. Now, for most structural properties, that could be beneficial, but it also means an increase in weight. So it's there are also question marks there. And then the final group is where more the structural design aspects are. So like one thing is the geometrical freedom, which can be an advantage, but also a disadvantage. So what if you're capable of printing an outer shell, what do you do with the internal structure, and how do you design it? Can it be optimized? Leaves all kinds of question marks, but this filament printing is also, usually it's a continuous line, so you have to somehow design the pattern that you can print in a continuous line. Some suppliers, very few suppliers, but some are capable of having a kind of stop and go system that you stop at one point, move the robot and continue at another point. But that is not the fastest and ideal printing situation. So it's still best if you can have a continuous print path. Reinforcement has been touched upon already by various previous speakers. It's a kind of the most obvious question, maybe. At least it was, especially in the first year when we were developing these printing technologies, one of the most asked questions I got from general public. Yes, but what about the reinforcement? And it's still not. I mean, there's a host of concepts being developed. We're going to have to see which one is best suitable to be integrated with the printing process. And another point that's also hardly really discussed yet is about detailing and connections between the print elements that you make. Obviously, they cannot have an infinite size. So how do we connect these elements together? So this is a whole bunch of problems that make it very challenging and interesting as a structural engineer to be involved in printing, concrete printing structural processes. project, sorry. So the two projects that I wanted to show a little bit more in detail is the bicycle bridge in Gemert. This was a collaboration between Dutch general contractor BAM, material supplier Weber BMX, Witteveen and Bos consulting engineers, and the TU Eindhoven. And then here you see kind of artist impression of what it should look like. It's very simple, but this was the first bridge in its kind, so we didn't want to make it overly complicated. And here you see an illustration of the structural concept. So the idea is that the big question mark on printed concrete is on the tensile strength and properties. So the idea was, okay, let's just make a fully pre-stressed structure. We print a couple of elements, we rotate them and put them together like a stack of books, and just press very hard so that the structure is always completely in compression, which gives us a more safe feeling about the whole concept. And the idea was that we print an outer surface with a kind of zigzag infill for the shear forces, but we can have pre-stressed tendons running through the cavities that are in between them. So we were considering what about ductility and structural safety of a design like that. So we have the pre-stressed tendons in one direction, which can also serve as a kind of as a reinforcement in that direction. And then additionally, we added in the transverse direction cable reinforcement, which is a system that we invented at TU Eindhoven a couple of years ago, which includes high-strength steel cable that is driven from a spool and then entrained into the concrete. We applied that at around 10% of the total amount of layers. And that gives this, I'm not sure it's very clear, but this kind of 3D image of the combination of the pre-stressed tendons in the longitudinal direction and reinforcement cables in the other direction to give ductility in both directions. And thereby sufficient structural safety. The whole structural design was based on an extensive amount of material tests, mechanical material tests in bending and tension and compression. Here you only see tension and compression, by the way, that were done over period of time at TU Eindhoven. That was the input, and Witteveen and Bos consulting engineers made a fully three-dimensional finite element model of this bridge, just to make sure that we were not overlooking anything and that there were no surprise peak stresses or things that could induce a failure, which is obviously not something you would normally do with a bridge of this scale, but nevertheless, this is something that we needed to be sure about. Then the question is, how can we get this approved? Because this is in the Dutch public infrastructure network, so it has to fulfill all the requirements, safety requirements, and it needs to get permission from, in the Dutch case, it's permission from the local municipality to get an approval. Existing Eurocodes do not allow this in the normal sets of rules. But fortunately, there's Appendix D of the EN 1990, which allows approval by experimental testing. So that is what we did. We did a 1 to 2 scale test, 4-point bending test on the whole on the bridge section, destructive test to prove that it would behave in a way that is safe, and also in a way that we predicted. okay, this was shown, and this was sufficient to convince the municipality that the bridge concept was safe and that it could be allowed in practice. So they gave the permission, and the bridge itself was opened in October 2017. Now the other project I want to show is a little bit more recent. It's 1 year old, and this was a pavilion that was made at the University of Innsbruck, where I was a guest researcher. So it's a collaboration between University of Innsbruck and TU Eindhoven, a 3D printing company, Incremental 3D, which is actually a spin-off from the University of Innsbruck, Baumiet, which is the material supplier, and POR, which is the contractor who put it together. The structure was only temporarily, and unfortunately I have to say that was already removed, which I feel is a bit of a shame, but yeah, that was the deal, and unfortunately the authorities couldn't be persuaded to do otherwise. But anyway, it's so in this team I did the structural design and engineering, and it was quite a bit more complicated than the bridge, because it consists of 47 different elements in a radial orientation. And this was a project that was completely designed and built in 11 weeks. So there was also not really time for experimental, for destructive testing. So I developed an approach that was, I felt should be safe. First of all the individual parts are self-supporting, so there's no reliance on any kind of arching action. The stresses should be below the concrete tensile strength, but even then there should also be reinforcement. Apply the material safety factor of 2.0 to be a bit on the safe side, but also a bit of a factor that was still manageable. Material properties were obtained from the supplier, but I have to note also that it is not exactly clear which methods they applied and how many samples they tested, and so that there's yeah, but before we can move this really into general practice, those kinds of things should be really much more standardized. And I performed a 2D finite element analysis on the section to design and check each individual element. Then the reinforcement, we opted for manual placement of reinforcement, basically because that was the only method available at the manufacturer. This picture on the left, by the way, is not from this project, but it does show the principle. So we had traditional reinforcement parts that were placed into the concrete, and then the robot continued printing after this was placed. Obviously, you want to do this as little as possible because it really disrupts the printing process. So each element has 2 layers in which the reinforcement is placed, so about 1/5 and 4/5 of the height of each element. And the elements are designed in a way that they are in principle capable of taking all the tensile stresses. So even if there are cracks in the concrete for whatever reason, the reinforcement will keep it safe. And then there was the issue, okay, so this was a very architecturally driven project. So it was the outer surface, the shape of the outer surface was really a given. That was like the architects gave it to me, and this has to work somehow. But I was given the freedom to design the inside as I saw fit, and that was that also gives you a lot of questions. Like what is a reasonable way of approaching that? In the end, I opted for some orthogonal inside because that is most easy to combine with the placement of the reinforcement, because we also didn't have complex bending equipment available. And then I also expected that it would give the least problems with the differential shrinkage and would allow for hoisting these elements into place, because that was also a question. So it gives a picture of something like this. You see one of the other elements. The red lines are the steel reinforcement bars that we placed in the critical areas. A couple of elements we applied in another more innovative way of reinforcement with carbon fiber reinforced plastic strands. And for instance, in this one, what you see here is that these strands, they can be shaped more easily into all kinds of free-form shapes. But I always wanted them to be a continuous circle or rectangle, because there was absolutely no data on the bond between the concrete and the CFRP strand. So basically, if you have a continuous circle, then even if there's no bond at all, then it will still remain in place, and there will be no failure from debonding. So that was a general rule for almost all the elements. There was one exception, and that was this element, which we called the table. And that is, well, you see it's actually very slim at the support side, and it's cantilevering quite a bit. So this was the one element that we had to put a lot more reinforcement in. And also we casted the open areas on the side. But what you see here, it's not a massive cast. This image could give that idea, but it was printed on this side, and then it was only a layer of about 1 to 2 centimeters thick that was cast on the bottom to give the element more stiffness. For this project, there was no external approval required from the municipality due to the size and the limited consequences. So this was approved on my professional experience, I guess, as a structural engineer, which I'm not so sure if that should be the way of doing things, but it did make life a little bit easier for this project. So that was the other project. I think there are two concerns that I want to raise when discussing structural engineering of layered extrusion 3D concrete printing. Well, the reinforcement is one thing, but that is something that you can design on forehand. But the concerns I have are in two other areas, and that is the first thing is quality control. So you see here just regular irregularities that occurred during the printing process, for which is not really a very clear reason, and this is a company actually that I think has the printing process relatively well under control. So if you're doing large-scale prints, it's not uncommon that the quality for whatever reason changes, and here it's quite visible. But who tells me that it doesn't happen also in more invisible ways? So that is really something that should be addressed. How do we make sure that the quality we get in an actual production print is really the quality that was stated also when you were doing material tests, for instance? And the other concern which I have, which also not very well, it's not discussed that widely, is curing and the shrinkage. We see a lot of the projects now that are just one-story buildings, and sometimes it seems that they assume that you can do that just by assuming that it's a compression-loaded structure, and therefore you don't need any reinforcement. But I think that's a very dangerous supposition, and we really should be aware of the sensitivity of these elements to shrinkage. They're not protected during curing, or we don't have guidelines yet on how to do it. I think they should be actually, but it's not a commonly defined practice. And the thin wall thickness of these printed elements, compared to massively cast elements, also make these structures much more sensitive to shrinkage cracks. And I mean, the shrinkage cracks like this is really, it means that it doesn't mean that you have a crack in your element. It means that you have two different elements that are, you know, that come together at this crack. But it's so it's really something to be aware of, I think, when doing structural design with this technology, and something that deserves more research. Then I'd like to close off with this promotional video, which I hope you like. So yeah, now here's some suggested reading of papers of where these projects are described in more detail. And that was it for me. Thank you.
Thank you very much, Freek. So I think your presentation was amazing. So I was reading some comments and some thanks to you from the audience. I think that it's a huge challenge to put everything together. So rheology reinforcement, and then see what you have designed, even though there are some critical points for the design. So thanks again.